Remember, this mid-year review is super important simply because it's important that we know everything that we've done since we started so that we could go on with the future. On this side here, we have the first mid-year review that we did last week. And that is the one where everybody kind of was getting everything wrong because naturally you all were forgetting everything. So you can see this mid-year review here is pretty much page for page almost the same kind of questions. And the reason why I did it is because this one is the one that you all are supposed to get wrong. This one is the one you all are supposed to get right. Yeah. So I'd really like to know how much of it you guys actually understand and got correct. You know, we're starting off with some simple computations, and we can see here that we have some fractions, and we're also dealing with BODMAS and such, right? So with BODMAS now, we know that we have to tackle brackets first. Right? So in the brackets here, we have 2 minus 2 on 3. Right? What if I take 2 and I say that that is 6 on 3, and 6 on 3 is 2, yeah? So 6 on 3 minus 2 on 3, and so my answer here is 4 on 3, right? So inside of the brackets here, I get 4 on 3. So now the problem becomes 1 over 6 plus a half times 4 on 3. Right? So we worked out the brackets to get 4 on 3. Now we do the multiplication first. So if it was division, we do that first because multiplication and division is the same thing. Remember BODMAS? I want you to think of this as the same thing as this. So it's really just 3 things you're looking for. Brackets first, multiplication or division second, and addition and subtraction third, right? So we do the multiplication, so you can see here that 2 could go into 4, and we'll get 2. So now it becomes 1 over 6 plus 2 over 3. Yeah. And 1 over 6 plus 2 over 3. 1 over 6 could what can 1 over 6 be expressed as something over 3, or maybe 2 over 3 could be expressed as something over 6. Right? If I multiply this by 2, I'll get 4 over 6, right? So what about 1 over 6 plus 4 over 6? Right? Isn't 4 over 6 the same as 2 over 3? Right? So what I did was I just converted the fractions so that they have the same decimal place. And now we get the answer as 5 over 6 is the final answer here. So so did anybody get 5 over 6? Shazay, you did it?
Yes, sir.
Alright, Scotia, you did it?
Yes, sir.
And you all got 5 over 6?
Yes, sir.
Did you guys use this method of me actually changing the form of the fraction?
No, I can't do that.
Why can't you though? You don't think it's an easier thing?
I feel like I'll mess it up. You can't, I don't know.
Right.
It's a thought process, I guess.
Yeah, well, let's try to adopt new thought processes, right? Look, because it's a real cool thing that I just did there, and it's you can see that being able to do it saves you a lot of time, right? So at the end of the day, if I want to minus this, if I could express this 2 with a 3 at the bottom, so you could see that if I have a 3 at the bottom, what should I have at the top to give me 2? So the answer is obviously 6, right? So 6 divided by 3 will give me 2. So now I have 2, but I have it in the form of a fraction, 6 over 3 minus 2 over 3, right? So now that makes now I can just minus the thing to get 4 over 3, right? So now when we take the 4 over 3 and multiplied it by a half, you know, we ended up getting 2 over 3, right? So now I have 1 over 6 plus 2 over 3. Yeah? And the 1 over 6 plus 2 over 3, well, first I was thinking, can I take this 6 and reduce it to a 3? And I mean, I could go 1 over 2 times 3, but that kind of gets it messy. So going smaller might be a problem, because you can see here this is 2 on 1. So getting bigger seems to be easier than going smaller, right? So maybe I could express this as 3. 3 times 2 will give me 6. So therefore 2 times 2, right, is 4. Right? Now you would think that we're changing the equation if we multiply just this by 2 and not this. But really we're not, because these two are the same fraction. Exactly the same fraction. Yeah? So I didn't change anything, I'm just expressing it in a different way. So Shazay, you kind of see how, do you understand what I just did there? Obviously we need to do the brackets first. And the brackets have a little bit of a BODMAS there. We have a division and an addition. So we know from BODMAS we do the multiplication and division first, right? So if I take the 2 on 8 and I multiply it by 2 on 1, because remember I have to take this and flip it. So it's an invert and multiply. So now this 2 could cancel with this 2 to give me 4. And of course this 2 will cancel with the 4 to give me a half. So this entire thing works out to be a half plus a half. So that works out to be 1. So therefore this works out to be 4 multiplied by 1, which is 4. So I guess no conversion there at all. Right? So but did you all get 4 for this one?
Yes, sir.
Alright, nice. And of course we're dealing with talking about some laws of indices here. So when you're multiplying, you add your indices. So this should be 5, I believe. This should be 3, because 6 times 3, you multiply the indices when we hear. Caitlin, you're keeping up with us? Because I know I might be going a bit fast. Alright, nice, good job. When you're dividing, you minus your indices. So 16 minus what will give me 7?
9?
Yes,
Yeah.
16 minus 9, okay. Yeah, I've been teaching all day, so I might have them little brain hiccups, you know. And of course, this one here, well, we have to assume that this is to the power of 1. So obviously 13 minus 12 will give us the power of 1. And there are other ways, there are other ways that we could look at this. If we have q to the 13 all over q to the 12, well, 12 of these will go into 12 of these, which will only have 1 left, right? So we have different ways that you can look at these things. Standard form, I mean, standard form isn't really a particularly important topic, but you do get it in the paper 1. Is a short question in the paper 1. So it's good to at least get it marked. So you just take this as 3.0 and you move the thing 4 spaces, 1, 2, 3, 4. So you get 30,000 here. Over here, you move this 2 spaces, 1, 2, so this will actually be 310. Over here, this goes 4 spaces, 1, 2, 3, 4. So that is what, 68,300. Right? Over here, if I was to take 8.0 by 10 to the 1 to negative 3, this here I'll take it as 3.2 by 10 to the, if I have the point here, 1, 2, 3, negative 3. Over here I will take this as 6.2 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8, negative 8. And this one looks really long, 2.1 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8. This is messing up my eyes, boy. 9, 10, 11, 12, 13, negative 13. So, anybody got anything here wrong? You all got these correct?
Yes, sir.
Alright, nice. So you see, this is exactly what I had planned. Is that that you all would have got a whole bunch from the first one wrong, and then this one, you know, and this is what the review is about, reminding us of stuff. Make x the subject of the formula. I hope that you all did all of this. Now, we see here x cubed minus 4 is equal to 5y. We have to make x the subject of the formula. So I'll throw over the 4. So x cubed is equal to 5y plus 4. And then x is equal to the cube root of 5y plus 4. And this here is your answer. Did you all get through with this one?
Yes, sir.
Yes, sir.
All right, nice. I like all of these yeses that I hear in here, boy. This is some good stuff, right? In this one here, I have a is equal to pi x squared, so it looks like an area formula. So let's call pi x squared is equal to a. So now I can see that x squared is equal to a divided by pi, and therefore x is equal to the square root of a divided by pi. And next, yes? Yeah?
Yes, sir.
Yes, sir.
All right. We'll call this like today is yesterday. You get it? Yesterday. Yeah. No, okay. All right. X the subject of the formula. Well, this one should be easy. X I have no squared there, so we don't have to do no funny business, right? So let's rewrite it as u squared plus 2ax is equal to v squared. If you ever do physics, this is an actual formula that you will have to learn. This formula has to do with speed and velocity of a fallen object, like a missile or something. You'll have to do this in A-level maths and in physics. In O-level physics, you'll just have to do this actually, right? So yeah, we want to make x the subject of the formula, so I'll throw across the u squared. So I'll have 2ax is equal to v squared minus u squared. Right? And then I'll take the 2a and I'll throw that across. So now I have x is equal to v squared minus u squared all over 2a. Yes?
Yes, sir.
Yes, sir.
All right. And then this last one here looks a bit tricky, but they can't fool we. We have the cube root of x over k, right, is equal to w. So how do we do that? Well, to throw over the cube root means that we are actually going to cube the whole thing. So this is going to be w cubed. Yeah, so therefore x is equal to kw cubed. Yeah?
Yes, sir.
Yes, sir.
All right. Like I'm gonna get some yeses for this whole paper, boy. Nice. So I'm glad that you all are actually responding to the mid-year review positively by giving you the same type of paper twice. So the first time you get to be unsure about it, and the second time you get to be sure about it, right? So we have the same kind of business here. I hope to get some more yeses for this one. The sum of two consecutive even. Oh my goodness. This here is something we never saw before. Is this. What are the integers? Because I know two consecutive integers will be like 23 plus 24. So that could be like x plus 1. Yeah? But how do I express two consecutive even integers? How do I make sure that both of them are even? Add 2. Alright, so what you're saying here, like let me just say I had 22, right? That's the first even number. The next even number will be 24. So obviously you're taking this here and you're adding 2 to get the next even number. That is what you're saying, right?
Yes, sir.
So therefore, if the first number is x plus, then I'll have to add 2. So this one here will be x plus 2. Is that what you're saying there?
Yes, sir.
Right. My question is, how can you guarantee that this x is even in the first place? Huh? What if this number here was odd? What if I put 5? Well, then 5, this here will be 7. So my whole thing will end up odd. Right? So what guarantees do I have that this x is actually even? What is one of the, and it's really boiled down to primary school thing, you know. What are one of the things you know for sure about an even number? And if you multiply anything by 2, it'll obviously become even.
Yes, sir.
Anything multiplied by 2, even, and so if you want to make sure that x is even, this first number here, you make it 2x. Right? Anything multiplied by 2. So even if I put an odd number inside of there, it multiply by 2, so that will make it even. You understand? So therefore, in order to ensure that the first term is even, you multiply it by 2. So now we sure that that first term is even, and therefore the next term will be 2x plus 2. And
Yes, sir.
right. So imagine now if I plug in a 5 in there. Right? If I plug in a 5 in there, then 5 times 2 is 10. So we sure that this first number is even. And well, we know 2x is 10, so the next number will be the 10 plus 2, which is 12, eh?
Yes, sir.
Right? You're sure you're good, right? All right, yes, but that's okay. That's okay. So these are the kind of things that this is the way that you need to start to think, right? And I do believe that you guys already do think like this. So all of these nice little things here is good things to look out for, right? And you see that is a piece of primary school magic that I use in terms of ensuring. How do you know that this first number is even, right? So this here now is equal to 106. So therefore, I could remove the brackets. So 2 and 2 is 4x plus 2 is equal to 106, right? 4x is equal to 104, 106 minus 2, right? So x is equal to 104 divided by 4, which is 26. 26 is not the answer though, right? 26 is just x. So what are the two even numbers, consecutive even numbers that will give you 106? Well, 26 times 2 is 52. So this first one is 52, and well, this second one will be 54. And it makes sense. 52 plus 54 gives you 106. Now let's see the sum of 3, and this is the same kind of question. The sum of 3 consecutive odd integers is 189. Right? What are the integers? 3 consecutive odd integers. So how could I ensure that this first number is odd? Well, right. So they're saying the sum of 3 consecutive odd integers. So odd integers could be 15, 17, 19. Yeah? Them is odd integers, and they're consecutive. Right? And we could see here that to get 15, you just add 2 to get 17. And then you just add 2 again to get 19. So it comes back to the same adding 2 thing. My question is, so to add 2, we will get the other numbers. How do we ensure that this first number is odd? Very good. No? Well, yeah. You could do 2. I was going to go 2x minus 1. But yes, 2x plus 1 would work. Because we know that 2x is even. For sure, 2x is even. So if for sure 2x is even, then for sure 2x plus 1 will be odd. Yeah? Shazay, you alright?
Yes, sir.
Right? So this is the first integer. Right? That is the odd integer. Plus, we have the same integer, 2x plus 1, that's going to be added to 2 to give us the second integer, right? So this one, I add in 2 to give me this one, right? And now I had to take this one and add 2 to it. So I'm going to take that one, which is what? 2x plus 1 plus 2. And I'm going to add 2 to that to get my third integer. Well, imagine if I had 3 consecutive odd integers. Wouldn't I have to take this one and add 2 to get the next odd one?
Yeah.
And then I'll have to take this one and add 2 to get the next odd one? So does that answer your question?
Yeah.
Right, so at the end of the day, that's all that I did here. Was I took this first one and I added 2 to get the next one, and then I take this one, which is over here, and I added 2 to it to get the last one. Right, Shazay, okay? So now we could just expand away, now that we have everything. I really have no multiplications going on here. So we can literally just remove all of the brackets. 2x plus 1 plus the 2x plus 1 plus 2 plus 2x plus 1 plus 2 plus 2. And that is equal to how much? So now let's just add our x's. So we have 2x plus 2x is 4x and 2x is 6x. So that is 6x. And then we have 1 plus 1 is 2 and 2 is 4. 4 and 2 is 6 and 2 is 8 and 1 is 9. So 6x plus 9 is equal to 189. Okay? So 6x is equal to 180. Throw the 9 across and minus. X is equal to 30. Yeah. So now that x is equal to 30, we can actually plug it back into this original here. So 30 times 2 is 60 plus 1 is 61. So the first number is 61. The next number will be 63. The next number will be 65. And if we add 61 plus 63 plus 65, we get 189. A over 4 minus 1 is equal to negative 5. So A over 4 is equal to negative 5 plus 1. A over 4 is equal to negative 4. Therefore, A is equal to negative 4 times 4. A is equal to negative 60. 15 plus 3p is equal to negative 6. Throw the 15 across. 3p is equal to negative 6 minus 15, which is negative 21. So p is equal to negative 21 on 3, which is negative 7. Yes? Minus 5. So let me write it a little higher. Negative 5m plus 2 is equal to 27. Oh God, this baby thing. Negative 5m is equal to 25. M is equal to 25 divided by 5 is negative 5. Yeah? Yes? Yes. Yes. Shazay, yeah?
Yes, sir.
Caitlin, yesterday? Alright. Good job. Nice. So we have some more laws of indices here. And remember that when we said a to the m all over n, we have to multiply a to the m times n. But sometimes inside of the brackets, you could have different things. So you could have, let me just say, p to the a times q to the b times r to the c, all to the n. And of course, you have to multiply all of them. So it would be p to the a times n times q to the b times n times r to the c times n. Yes? And we actually proved all of these things. So I hope that nobody here asks, well, why does this work? Because we proved in class why it works, right? So I have, I'll do the brackets first because this BODMAS applies straight through mathematics, yeah? So 4 times 2, that is p to the 8th, and then 4 times 1 is q to the 4, being multiplied by q to the 5 times 2 is 10, and p to the 5. So now we add the like terms, so we can see this p to the 8 and p to the 5, well, they are being multiplied, so I can add it. So p to the 8, 9, 10, 11, 12, 13, q to the 14. So we have here a cube, b to the negative 2. Well, we know that a to the negative m is equal to 1 over a to the m. Right? So that's one of the laws that we know. So we could say, just for sake of argument, that this is 1 over b to the squared, but we don't need to. We could just leave it like this if we want to. Right? A cube b negative 2. And that's being multiplied by 4 2s are a to the 8, 4 2s are b to the 8. And that is equal to, now we just add the indices because you're multiplying. So a3 times a8 is a to the 8 plus 3, 8, 9, 10, 11, a to the 11. And of course 8 here plus negative 2 will be 8 minus 2, which is 6. Negative 6. Remember what we're doing is we add in indices. So this is negative 2. Right? This is b to the negative 2. Remember, multiplication is commutative. So I could just take this b and multiply it by this b over here. So it's b to the negative 2 times b to the 8. You add your indices. So that's b negative 2 plus 8. Negative 2 plus 8 is the same as b to the 8 minus 2. Now, when it comes to separation, you have to understand, like say if I have 3 plus 2 all over 5, right? This means 3 over 5 plus 2 over 5, right? So when it comes to separation, you have to take your this here denominator as one thing. So like let me just say I have 3 plus 2 all over 5 plus 3. 5 plus 4, right? If I wanted to separate this, I could only separate the numerators. So it would have to be 3 over 5 plus 4 plus 2 over 5 plus 4. You have to keep your full denominator, right? So let's see if separation actually does anything here to help us, right? I'm not sure if separation will. This will be x to the negative 1 over x plus y plus y to the negative 1 all over x plus y. Okay. So what is... But I have an easier way to do it, you know. Let's not separate, right? I have an easier way to do it. Let's just leave this as x plus y, right? And we have this x to the negative 1 is 1 over x. Right? And this y to the negative 1 is 1 over y. Interesting. 1 over x plus 1 over y. Is there, and it would have been nice if I could have pull out an x plus y over here, you know, and then be able to cancel off the integers. Do you think it have any way I could do that? Right? Let's work out the top, right? I could say that 1 over x plus 1 over y is, I had to multiply, so I'll get xy, right? And then this here is, the x's cancel, so I'll get y, and then the y's cancel, so I'll get x. Right? So therefore, 1 over x plus 1 over y is actually equal to x plus y over xy, all divided by x plus y. All you understand how I got from here to here?
Yes, sir.
Okay.
Right? So Of course, this y plus x could just easily be written as x plus y, because y plus x and x plus y is pretty much the same thing. So now, this is interesting here. Right? Now, what do we have? We have x plus y divided by xy. That is being multiplied, all being multiplied by 1 over x plus y. Make sense?
Yes, sir.
Right? Because if I have 3 divided by 2, that is the same as 3 multiplied by 1 over 2. Yeah, you could see that everything that I am doing in algebra, I should be able to back it up using an arithmetic example. If you can't take using the arithmetic example, if you can't express it in this way, then once you could do it with arithmetic, you could do it with algebra. And now we could see that these x plus y will cancel with this x plus y. And now we have 1 over xy is the final answer. There, you didn't think about actually adding this to get that, right? You know why I thought about that? Because I really hated this x plus y under here, and I was hoping that I was hoping that it would be great if it had some way for me to pull x plus y out so that it could cancel with that. And I was starting to wonder if there is a way to do that, where I could, because I'm noticing that it have a lot of things in common. You have an x here, you have a plus here, you have a y here. So maybe it have a way to pull out that x plus y so that it could cancel with it. And I started to think factorizing it. But how could I possibly have 1 over x plus 1 over y? How could I pull out x plus y? X plus y multiplied by what will give me 1 over x, 1 over y? Right? That is a hard thing, because apparently x plus y multiplied by 1 over xy will give you 1 over x, 1 over y. But this is a hard thing to imagine. So how I started to think about it, Scotia, is that I wanted to get rid of this denominator. And I wanted to cancel it off with x plus y on the top here. But I didn't know how to factorize it. So I say, you know what? Let me try adding it. Maybe actually adding it might give me a way to cancel it off. And look, it did. You see that, Scotia?
Yes, sir.
Right? So that is essentially the thought process that I used there. What about this one, Caitlin? Any luck with this one? This one is a lovely one. Oh, wait, what's the final answer again? 3 is the final answer again. Wow. Well, that seems like a pretty definitive answer, right? All of the ends magically gone. All right, so let's see. Scotia, any ideas for this one?
I got 2.
You got 2. Shazay, tell them how to do this one. Remember, when we're working with indices, Shazay, the base number 2 to the 3 times 2 to the 4. So this base number has to be the same, and
Yes, sir.
in order for us to play with the indices, right? In order for us to play with the indices, so the base number has to be the same, and then we could say, well, that is 2 to the 3 plus 4, which is 7. They go saying?
Yes, sir.
So the base numbers here are not the same, but maybe we could make them the same, right? The base numbers here, 10 and 4, those aren't the same, so we can't play with the indices at all. But what if we could make them the same, right? So the 4 to the n, what is 4? 4 is 2 squared, eh?
Yes.
Right? So 4 to the n is really 2 squared to the n, eh?
Yes.
Right. So, and when you have this, I could take this and multiply it by the indices, so I'll get 2 to the power of 2n, eh?
Yes.
Right? So we see here that this 4 is 2 to the power of 2n. Nice. And it being minus 10. Well, 10 is really 5 times 2, eh? That is 5 times 2 to the power of n, eh?
Yeah.
So that is 5 to the n times 2 to the n. Make sense?
Yes, sir.
Alright? So, for 10, I could have 5 to the n times 2 to the n. Right? And even though you can't really make that, I wonder, you know. I wonder if Shazay might have been right, you know. Right? Because by the same way, yeah, but it's a multiply. You see, I could do that if it's 5 times 2 to the n. I could do that. Right? But if it's 10 minus 4, all to the power of n, I can't say that is 10 to the n minus 4 to the n. No, that don't work. It had to be a multiply or a divide, right? If you, in terms of your laws of indices. Okay? So I have that there now, right? Divided by 5 to the n minus 2 to the n. Well, look at that. And things starting to look a little bit familiar now, ain't? Right? Things starting to look, you know, like, so what if, because again, I hate denominators, right? So if I could get rid of this, cancel this denominator off, right? So if, in order for me to cancel this denominator off, this denominator is 5 to the n minus 2 to the n. So I would kind of need to get 5 to the n minus 2 to the n upstairs. Yeah? Upstairs. And we almost there. We almost there. I have the 5 to the n on this side. But after the minus side, I need a 2 to the n. I have 2 to the 2n. So, what is there any way that I could change this to involve having 2 to the n somewhere inside of here? What if I have the 5 to the n times 2 to the n minus, what if we had 2 to the n squared? Do you agree? Because remember, it started off as 2 squared from the 4. We got 2 squared to the power of n. And then I multiplied that to get 2 to the 2n. But remember, multiplication is commutative, so I could switch these two. So I could have 2 to the n squared. And if I multiply 2 by n, I'll still end up with 2 to the 2n. Right? Alright, so here what, right? Let me just do a little recap of how we reached there so far, right? I see in here that I have all different base numbers, so I can't do nothing with the indices. So I figure, well, maybe I could reduce some of them to see if I could get the same base number. I can't reduce 2, and I can't reduce 5. 5 don't really have any factors, 2 don't really have any factors, right? But I could reduce 4 and 10, right? 10 turned out to be 10 to the n. I could say that is 5 times 2 is 10 to the n, right? And 4, I could say 4 is 2 squared to the n, yeah? And now I could see things starting to shape up. 5 to the n minus 2 to the n. Okay? Now I could expand this out, n and n. So that means that I'll have 5 to the n times 2 to the n. And then this will be minus, this n times 2 is 2 to the 2n. Right? And that is over 5 to the n minus 2 to the n. So I almost have the denominator upstairs. I had the 5 to the n on this side of the minus sign, but I need the 2 to the n to be on this side of the minus sign. So I'm going to manipulate this guy. That guy over there, I'm going to manipulate it. So I'll say, well, okay, 5 to the n times 2 to the n, and this is all over 5 to the n minus 2 to the n. This is going to be minus 2 to the n squared. Right? You notice what I did there, right? 2 to the n squared by the laws of indices means that I take this 2 and I have to multiply it by that n. So I'll get back the same thing, 2 to the 2n. That is because 2 to the n squared is the same as 2 squared to the n. Right? This is a point that I tried to make in the last class. Right? Because multiplication is commutative, so it doesn't matter which order these numbers are in, it'll still work out to be 2 to the 2n. Right? So you all have a clearer vision now as to how I got this? Alright, so watch, 5 to the n times 2 to the n minus, guess what? 2 to the n squared. Isn't 2 to the n squared really 2 to the n multiplied by 2 to the n? Does that make sense to you all? And 5 squared is 5 times 5?
Yeah.
Right. So 2 to the n squared is 2 to the n times 2 to the n. Right? Divided by 5n minus 2n. So now I could see I have the 5n on this side of the minus sign, and I have the 2n on this side of the minus sign. So now I could pull it out. So divided by 5 to the n minus 2 to the n. If I pull out 5 to the n minus 2 to the n on the top, right? What will I have to have here now? 5 to the n minus 2 to the n times what? What will I have to multiply in order to get this? In fact, you know what? No. Look. An easier way to look at it. What do I have in common? 2 to the n on this side and 2 to the n on this side, right? Yeah? So I could pull out the 2 to the n. If I pull out the 2 to the n, open brackets, 2 to the n times 5 to the n will give me 5 times 2 to the n, right? Minus 2 to the n times 2 to the n on this side will give me 2 to the n times 2 to the n. So now these two could cancel, and your answer is 2 to the n. So you could see in my thinking, what was my thinking? Well, my thinking was, yo, I have to have the same base numbers if I want to play with the indices, and I don't have that, right? So I'm noticing similarities, though. I'm noticing 4 have something to do with 2, and I'm noticing 10 have something to do with 5. So I say, well, you know what, let me try to manipulate the base numbers and maybe something could happen. I can't manipulate 2 because 2 could only break down into 2 times 1, and that doesn't really help me that much. 5 could only break down into 5 times 1. That doesn't help me at all. But I could break down the 10, and I could break down the 4 into 2 squared. And now I'm starting to see similarities. Well, look, the denominator have 5s and 2s, And now the numerator only have 5s and 2s. Well, that is starting to encourage me. So I expanded out all of the n's, and I say, well, wow, well, look, now it's looking more and more familiar, and really and truly it's chances that are taken, right? I just need to get rid of this 2n, because I don't have anything with 2n under here. That 2n kind of messing up stuff. I just want n. So that's when I remember, well, hey, according to the laws of indices, this is the same as this. Yeah, just 2 times n. Right? And guess what? This is the same as this, because n 2 to the n times 2 to the n. Yeah, add your indices, so you'll get 2 to the 2n. So at the end of the day, it really boils down to knowing your laws of indices here. This is a lovely, very lovely question. Okay, so this is 5x to the 5y squared times 3 open brackets x y cube close brackets all squared all over 15x squared y. All right. I can't take this 3 and multiply it in brackets because this brackets is square. So I'll expand this. So that's going to be x squared and y to the 6. So that is 5x to the 5y squared times 3x squared y to the 6 all over 15x squared y. Are you cool with that so far?
Yes, sir.
Alright. So you see, after I expanded that 2, well, then the 3 is just multiplied by it. Alright? So you can remove the brackets one time. Now let's work this denominator. It's all multiplied. It have no additions and thing there. Everything is multiplication. So I can just literally take this 5 times this 3, that's 15. Right? X to the 5 times x to the 2 is x to the 7. Y to the 2 times y to the 6 is y to the 8. And that's being divided by 15x squared y. Of course, this 15 gone here. 2 of these will go, so I'll have x to the 5. And then 1 of these will go, so I'll have y to the 7. So the final answer is x to the 5, y to the 7. That. So let's call the current C, right? And an electrical conductor varies inversely as the resistance of the conductor R. So it varies inversely means that C is inversely proportional to 1 over R. Right? Varies inversely. So that means that I can actually make my general equation. C will be equal to K multiplied by 1 over R. So C is equal to K over R, where K is a constant of proportionality. So K doesn't change. K just works out to be some constant number. Right? Everybody okay with this so far? So now we have a general formula. Let's read. And now they will give you some information where you could find K. So if the current is 12, when the resistance is 240 ohms, so I'm not even gonna read. I don't know that they actually given me information where I could find K. So K is equal to 12 times 240, which is 240 times 12 is, so K is 2880. So now the particular equation, or the specific equation, is 2880 over R. Right? That is the relationship between current and the resistance. What is the current when the resistance is 540? Well, the current is 2880 divided by 540, which is 5.3, about there. Yeah, 5.3, yeah?
Yes, sir.
Alright, nice. And I believe that this is our last page for the night, and from here we will carry on with this on Saturday, right? So, at the end of the day, same kind of thing from last time. We could see here that this number inside of this bracket is the same as this number inside of this bracket over here. So we could now just cancel this and this. So the answer for this is x plus 1. Right? We have to add these two the old-fashioned way. So v plus 3 over 2 plus 2v plus 1 over 5. Right? We multiply your denominators. 5 times 2 is 10. Right? 2 into 2 is 5. So 5 multiplied by this is 5 into v plus 3. Of course, you know, I already told you the cross multiplication method. 5 multiplied by v plus 3, and then 2 multiplied by 2v plus 1. So I get 5v plus 5 3s are 15 plus 2 2s are 4v plus 2 all over 10, which is 5 and 4 is 9v plus 17 all over 10. And if I have nothing I could factorize, I don't have no factors of 9 and 17. There is nothing that I could do there, no cancellations. So this is the final answer there, yeah? That you would have tackled these two very well. Of course, this is the same thing in terms of cancellations here, because everything is being multiplied. If it had, oh come on, stop it. If it had an addition sign here, then you couldn't have cancel things off like mad, right? If it had an addition sign anywhere in here, you couldn't cancel things off. So this x plus 2 will cancel into this x plus 2. So I will now get x plus 3, x minus 3 over x plus 9. I mean, that 3 and that 9 seems a bit too close. Is there any way? What if I had x minus 3 on top? If I had x minus 3 on the underneath, what could I multiply in order to make this x plus 9? Anything? Is there any way that I could cancel anything like this, or is this the final answer? I don't think there is anything, because I could think that there is negative 3. Negative 3 multiplied by the negative 3 will give me plus 9, yeah. But negative 3 times x will give me negative 3x, and I don't have that here. Yeah. So at the end of the day, this here is actually the final answer. If you wanted to, you could have split it up like this, right? But I don't think that. I think that this is the simplest way it could be. Yeah. So x minus 1 over x plus 3. Did you just say 3 into 3, 1, 3 into 9, that?
Yeah.
Right. You could have done that if it was x over 3x. Oh, sorry. If it was 3x over 9x. Then you could have do that. Multiplication is things you could do that with. Yeah? But addition is something totally different. Addition actually separates things. So this 3 here, this x here, is separate from this 3. And this x here is separate from this 9. Right? And you can't say, what you attempted to do was you attempted to say x minus 3 all over x plus 9 is x over x minus 3 over 9. That's kind of what you attempted to do there. You know, that was your understanding of it. And that way you could have done that. But no, fractions do not split like that. Right? You can only split them by the numerator. And the denominator must remain intact. So you'll actually get this. You understand what you did wrong, Squisher? Right? It's really important that we get things wrong. It's important that we get things wrong, especially things like that. Yeah. We have two just simple distribution stuff in terms of expanding the brackets, and that will be the final questions for today. So we have this entire thing multiplied by the first term, which will be 2y over x multiplied by x plus 3y. And we have a minus. We have this entire thing multiplied by the second term, 1 over 12 into x plus 3y. Yeah. So now we can actually expand these brackets now. So this multiplied by this, right? That is 2y over x multiplied by x over 1. So the x's will cancel, right? So this here will be 2y, and this multiplied by that. And then this multiplied by this will be, that is 2y over x multiplied by 3y over 1. So that will be 2 3s are 6y squared all over x, right? So that is what we get for that expansion there. And now for this one, we have minus 12 times x, which is minus x over 12. And then this minus 1 over 12, sorry, times 3y is 3y over 12. Well, the negative is there. And then 3 into 12 is 4. So we end up getting minus y over 4. That is 1 over 12 times 3y, right? Negative y over 4. I hope I'm not going too fast. Anything that we could do here in terms of, I mean, I have y's and y's over here, right? I think you know, we could simplify it a little bit, but if you had this fair answer, that shouldn't be no problem, right? But remember, this is 2y plus 6y squared on x minus x on 12 minus a quarter y. Y on 4 is a quarter y, right? So 2 minus a quarter is 1 and a quarter. So we have 1 and a quarter y, 4, 5, 1 and a quarter y, 4 times 1 is 4 and 1 is 5. So that's 5 on 4y, which could also be written as 5y on 4. 5y on 4. Right, so them 2 y's go on there. Right, that's 2 minus a quarter. That is give us 5 on 4. And now this, I mean, maybe I could, I can't say that I could pull out x. Let me ask you something. Do you think that this x is the same as this x? And you know how this y here is the same as this y? So we could minus and add them. Right? Do you think that this x is the same as this x? Yes or no? No, the positive and negative don't matter, because this is a negative here and this is a positive here. But the fact is that this is y and this is y. So I could have taken the 2 and the minus a quarter and get my 5 on 4, right? 5 on 4y, right?
Yes, sir.
So can I do the same thing with these x's? Is this x the same as this x? Right? The answer is no, they are not the same x, right? Because if you really think about it, what is this? This is 6y squared multiplied by 1 over x, isn't it? And minus x on 12. Or we could actually write the x on 12 as 1 over 12 times x. Right? So this is 6y squared multiplied by 1 over x, and the laws of indices says that 6y squared 1 over x to the power of 1 is the same as x to the power of negative 1. Right? So you could see here that we have an x in the denominator and we have an x in the numerator. When we were dealing with the y's, we could have actually added this y to this y because it was both the same kind of y to the power of 1, y to the power of 1. But we can't manipulate these because they're not the same kind of x. Because this x is in the denominator means that it's actually x to the power of -1. And then on this side we have x to the power of 1. So because they have the different indices then, right, we can't add them. We can't do anything. Remember, if you have x plus x squared, you can't do anything with that. Yeah? Right? Especially when it comes to adding, because you notice your laws of indices have to do with multiplication. They don't have to do with addition. Right? You can't add the indices there or anything. There is nothing you can do here. This had to remain so. Yeah? So same thing here. We have two different. So do you guys understand why it's different x's? The reason why I asked the question is because I was wondering if maybe it had a way that I could have grouped this by pulling out x now. Pulling out x, factorizing it, maybe having x on the outside and maybe only something with y on the inside. But no, it's two different kinds of x's. X to the -1 and x to the 1. Caitlin, you understand what I say there? So the final answer for this would have probably been 5 on 4y plus 6y squared on x minus x on 12. And you could leave this as the final answer. If you want, you could group these and pull out the y. Yeah? So I could pull out, this is y into 5 on 4 plus 6y on x. You could do that, but it doesn't make it any easier. Right? So at the end of the day, this is your final answer. Yeah? No? Scotia, you do up to there?
I just want to up to second line.
That is fine. That is fine. If you got up to the second line, no problem. But remember, this 2y could minus from the y on 4, yeah? And that is the only extra step. Okay, guys, so that was it for today.